Ehkki Victor Changi nimeline instituut Sydneys tegeleb kõikvõimalike südameprobleemide uurimisega, on see ainus kogu Austraalias, mis keskendub südamelihase haigustele. Lihtsalt öeldes avaldub südamelihase haigus nii, et inimene hakkab ka kõige väiksema füüsilise pingutuse korral, näiteks trepist üles minnes, kõvasti hingeldama. Kõige raskemal juhul vajab patsient uue südame siirdamist. Just siin instituudis töötab molekulaarkardioloog Siiri Iismaa, kelle töö peamine eesmärk on praegu õppida kasvatama uusi südamerakke, mille kohta varem arvati, et see on võimatu.
Me püüame aru saada, miks südamehaigused juhtuvad, mis molekuulid on tegevuses selles protsessis. Et siis me saame kas takistada südamehaigust või isegi ära hoida südamehaigust.
Canberras sündinud Siiri Iismaa on teise põlve väliseestlane. Tema mõlemad vanemad töötasid meditsiinis ja see mõjutas laste karjääri valikut. Pere kõik 3 tütart on täna seotud teadusega. Tõsi küll, Siiri alustas põllumajandustaimede geeniuuringutega ja tegi seda vägagi edukalt. Tema nimel on tänini näiteks mitu ristikheina patenti. Hüppe agronoomiast südameuuringutesse polnud nii suur kui arvata, sest proteiinide tasandil on seosed samad. Legendaarse südamekirurgi ja Austraalia südamesiirdamisprogrammi algataja Victor Changi järgi ristitud instituut loodi Sydneys 1994. aastal ja Siiri Iismaa oli üks selle esimesi töötajaid. Täna töötab siin majas 160 inimest.
So we now span research all the way from the very molecular, from, for example, looking at structures of proteins using fancy tools like X-ray crystallography, all the way through to clinical trials in patients.
Instituudi tegevjuht on professor Robert Graham. Labori igapäevatööd juhib Siiri Iismaa.
And she has made a huge difference to this institute and has been a rock, a solid person that I can rely on, and has really led the research that my laboratory does over many, many years. So I'd be lost without her. We like to do what I call Rosetta Stone research. That is research that will be here tomorrow, not something that you do and then a few days or weeks or years later it's overturned by something else. We like to do very solid biological research that really is maybe only makes a small step, but is a step that will be here for in perpetuity.
Siiri Iismaa täpsem uurimisvaldkond on nii spetsiifiline ja eesrindlik, et Eestis ei tegele sama asjaga teadaolevalt keegi. Aga et lihtinimene midagigi aru saaks, tuleb kõigepealt alustada ABC-st. Ehk, mis on süda ja kuidas ta töötab?
Südamelöögid tekivad südame alumises pooles asuva kambri kokkutõmbumisel. Neid kambreid siin nimetatakse vatsakesteks. Ja vatsakeste kohal paiknevad kojad ehk aatriumid. Ja veri pumbatakse paremast vatsakesest kopsudesse ja seal ta rikastub hapnikuga. Ja kopsudest läheb veri südame vasakuse kotta ning edasi selle all olevasse vatsakesse. Ja vasakust vatsakesest pumbatakse veri keha suurimasse veresonde aorti ja siit läheb veri laiali üle kogu keha, andes ära hapniku. Nüüd hapniku vaene veri suundub tagasi südame paremasse kotta ja sealt paremasse vatsakesse, olles jällegi valmis siirduma kopsudesse. Ja üks vereringe võtab umbes 23 sekundit.
Süda on ainus organ, mis kunagi ei maga. Ta lööb keskmiselt minutis 70 ja päevas 100 000 korda. Iga kokkutõmbega lööb see pump ringlusesse 70–100 milliliitrit hapnikuga rikastatud verd. Selle tulemusel tekib kehas vererõhk, mida saab mõõta. Tervel inimesel on see vahemikus 85 ja 130. Teadlastele pakub mõistagi huvi see, kui asjad on normi piirest väljas. Iismaa ja tema kolleegid on juba aastaid uurinud konkreetsemalt stressi mõju südamele.
For a long time we've been interested in how the heart is regulated moment to moment. So one of the very primitive responses where in times gone by is when we saw a big grizzly bear coming at us or a tiger. When you see that, you know that's danger, and that sets off a message in the brain that makes your heart work harder and faster to enable you to have enough blood supply so your muscles can work and you can run away. And those of us that have had a good system that's allowed that to happen efficiently have escaped the bear or the tiger and have gone on to have children, and they've also inherited that good system. So that works by the fact that the brain releases a chemical called adrenaline, and that adrenaline then acts on the muscle, on a heart muscle cell, and it interacts with a protein on the surface of the cell, and it tells the cell to, like putting your foot on the accelerator in a car, to work and to drive faster. So it drives the cell faster, the heart works better, and it gives more blood supply to the muscles, and then you can run away.
Ja mõnedes tingimustes stress on hea ja normaalne nähtus ja see aitab edukalt toimida ja isegi ellu jääda, kui on ohtlik olukord. Aga pikaajaline stress mõjub organismile hävitavalt. Ja vererõhk tõuseb, siis veresooned lähevad kitsamaks ja siis see süda peab rakendama suuremat jõudu, et suruda verd läbi soonte ja südamelihas suureneb või pakseneb.
So we've been very interested in those proteins on the surface of the cell with which adrenaline acts like a key in a lock and opens that lock to make the cell work harder. So that's been a very major part of my own laboratory's research, and Siiri has been a major player in helping us to discover exactly how the key fits into the lock and how we can open the lock once the key's in the lock and tell the cell to now work harder and faster. So that's a big part of our work.
Veel hullem kui pidevale stressile, mis piltlikult öelda südame gaasipedaali põhja surub, lisanduvad ka peremehe halvad harjumused. Suitsetamine, alkohol, ebatervislik toitumine ja vähene liikumine, mis omakorda võib viia veresoonte lupjumiseni.
See kõik on südamele lisakoormus. Süda peab siis rakendama suuremat jõudu ja südamelihas pakseneb veelgi. Selle tagajärg on, et südame seinad ei ole küllaldaselt varustatud vere ja hapnikuga ja südame töö kahjustub. Südamehaiguse oht aina suureneb. Ja pärgarterite ummistumine põhjustab südame isheemiatöbe, südameinfarkti ja südamepuudulikkust.
It's our number one cause of death and disability. We've made great progress since the 1950s and 60s when heart disease worldwide in the Western world, in the developed world, countries like Estonia and Australia, was killing over 1 in 2 people. It was an epidemic in that time. So now we've shifted the problem from being one of people dying acutely to many of them, unfortunately, even though we save them acutely, they go on to get heart failure. And now the problem is translated into a chronic problem. We can treat that to some extent, but if it gets very severe, the only ultimate treatment is a heart transplant. So that's what the Institute has particularly focuses on those illnesses that lead to heart transplantation.
Pole ka mingi ime, sest ehkki meditsiini areng on olnud tohutu, on südamehaigused nii Eestis kui Austraalias endiselt suurimad enneaegse surma ja invaliidistumise põhjustajad, saades saatuslikuks umbkaudu 1 inimesele 3. Victor Changi teadusinstituut tegutseb tihedas koostöös naabruses asuva St. Vincenti haiglaga, mis on suurim südame siirdamise kliinik kogu Austraalias. Just siin katsetatakse praktikas teadlaste leiutatud uusi võtteid.
This is our cardiac intensive care unit.
Kardioloog Peter McDonald on mees, kes puutub elu ja surma küsimustega kokku iga päev. Seetõttu lükkub ka meie esialgu plaanitud kohtumine 24 tundi edasi. Ühe siirdamise juures tekkisid komplikatsioonid, mistõttu pidi doktor intervjuu asemel tegelema värskelt uue südame saanud mehe päästmisega. What's the prognosis like?
Well, the prognosis is guarded, but I think optimistic. I think looking at the recipient today, I feel a lot better, a lot happier about the situation than I did yesterday.
So it was a scary moment.
Yeah, it's the sort of moments that we try and avoid.
1984. aastast on siin haiglas tehtud 800 südame siirdamist. See on üle poole kõigist siirdamistest Austraalias. Kardioloog Peter McDonald on osalenud neist 600.
These days heart transplantation has become almost a routine procedure. I guess you'd always hesitate to say it's routine because someone else has to die before someone can have a heart transplant. But the actual procedure itself and the expected outcome for the recipient and progress of the recipient is now generally fairly predictable, and most patients who receive a heart transplant would spend 2 to 3 days in the intensive care unit and 2 to 3 weeks in the hospital, and then they're discharged home, and then it's just progressive, steady recovery from then.
Kuniks siirdamine on ainus tegelik variant kulunud südamega inimest aidata, on keskendutud protseduuri lihvimisele. Just sellega on ka seotud instituudi senise ajaloo üks tähtsaim saavutus.
When you take a heart from the donor patient before you put it into the recipient who needs the heart transplant, you have a window of about 4 hours when the heart still remains healthy. After that time, you can't use the heart anymore. So that means if you want to take a heart from somebody in the north of Australia, Australia is a very big country, very different from Estonia. So if you want to go from the north of Australia, say from Brisbane to Melbourne, you can't do it because it takes too long.
My area of interest is in how to optimise the preservation of the donor heart during this critical period where the heart's taken out of the donor, and in the context of transplantation, the donor hospital can be in another state, so it can be anywhere up to 3,000 kilometres away in an Australian context.
So now for the first time we've developed a treatment. One of our people here, Professor Peter McDonald, has developed a treatment which can extend the length of time we can have the heart outside without being in a patient from 4 hours to close to 14 hours.
So our research really has been aimed at trying to protect, as I say, to protect the heart. One of the key sort of principles of heart preservation during a transplant is to keep it cold, like putting it in an ice bucket. But within the ice bucket there is a solution that the heart is bathed in, and we think the components of that solution are critically important to the protection of the heart, to basically keep it in, if you like, in almost a hibernating state, so it's alive and it's safe and not doing any work. So we've, over a period of the last 15 years, we've made a whole series of modifications to this preservation solution. We've tested it in a range of experimental settings to the point where we're now happy to apply it in human transplantation.
So now we virtually can get a heart from anywhere in Australia to anywhere else in Australia, or in Europe you can take a heart from Dublin to Ankara and still have a heart being successfully implanted. But it means we can also get better matches. The match you get, the genetic match, is very important, so we can get better hearts.
Well, I think it's significant in a number of contexts. One is that it makes the operation safer. There is heart transplants overall are a very effective operation, but there's still a 5 to 10% chance that this heart won't work once it's transplanted. So for the individual lining up for a transplant, that's a very significant risk, and we think we can not eliminate completely, but largely reduce that risk. If we can make it 1 to 2% rather than 10%, that's an enormous, I think that will be an enormous benefit. The other thing it does is that by improving the quality of the preservation, we can look more broadly at potential donor hearts. So there are some donor hearts now that we would consider not well enough or not strong enough to be used for transplantation. But I think with more effective preservation techniques, then that's something that we can start to look at. So there's the prospect of increase in the number of transplants that we do and therefore help more people.
Südame säilitamise õige retsept leiti just tänu molekulaaruuringutele.
I think it's critical to understand the molecular pathways which are involved in damage to the heart when the heart's taken out of its normal environment, when it's deprived of oxygen, when it's put in a cold environment. It's only when you understand the molecules that mediate these processes that you can develop drugs or other molecules to counteract them. So I think that's the critical sort of element.
Ja siinkohal jõuamegi ringiga tagasi Siiri Iismaa ja tema molekulaarkardioloogidest kolleegide töö juurde.
There's an enormous number of people in the community that suffer from advanced heart disease. Heart transplantation, although it's a wonderful treatment for people that receive it, it's a very limited option. It's limited by donor organ availability. We don't want more people to die so that they can become donors. We want to find an effective alternative to heart transplantation. And I think regenerative therapies where we're looking to grow new mice, heart muscle cells, to the extent that you can replace a failing, damaged heart, I think that's a very exciting and very important area of ongoing research.
Pikki aastaid keskendusid Iismaa ja tema kolleegid adrenaliiniretseptorite toimimise ja südamehaiguste seoste uurimisele ning tegid nii mõnegi olulise avastuse. Konkreetne proteiin, mida Iismaa aastaid uuris, kannab nime TG2. Üllataval kombel avastati näiteks, et sel on roll ka mujal kehas peale südame. Muuhulgas saab selle omadusi kasutada ajuvähi vastu.
The nice thing, interesting thing about basic research, molecular research, is the same molecules that are used in the heart are used in other tissues. And this particular molecule that is, if you like the tie rod between the accelerator and the engine in a car, that same tie rod is used in other cells like brain cells, and a defect in that tie rod in the brain can lead to brain tumours. So she's studying that from that point of view. So we started off studying the heart, and it ends up, because you're working on molecules, that same molecule can lead you to discoveries that relate to the brain and to brain tumours, which is sort of fun. Sometimes you can go so far. I mean, you work in heart disease and you then collaborate with colleagues, and that's what Siiri's doing with a group over at another hospital, and she's working on these brain tumours, particularly in children. So they're very nasty tumours in children. But it turns out our work helps them to progress.
See tähendab, et kuigi te uurisite südame tegevust, siis õnnestus selle käigus avastada üks väga huvitav reaktsioon või mõju, mis puudutas hoopis ajuvähki.
Ja.
Ja see võib-olla on palju perspektiivikam üldsegi, kui see rakendus seal südames.
See lihtsalt näitab, et see proteiin on tegevus mitmes kohas, mitmes elundites ja süda on üks koht ja peaju on teine koht.
And she has been instrumental in opening up our understanding of how that protein not only works in the heart to regulate heart function, but works in the brain and works in other tissues. So that's the work that she does.
Aga nüüd on sihikul uus ja palju, kui kasutada banaalset väljendit, seksikam hüpotees, mis kasvas välja sellest samast retseptorite uuringust. Inimkeha on imeline aparaat, mille taastumisvõime on kohati hämmastav, aga on mõned erandid. Näiteks südamerakud ei pooldu enam pärast inimese sündi. Muuhulgas tähendab see, et pärast infarkti on südamevõime taastuda väga piiratud. Südamelihase rakud ei saa poolduda, sest geenid, mis nende paljunemist reguleerivad, on välja lülitatud. Miks nad on välja lülitatud ja mis seda protsessi reguleerib? Sellele otsivad nüüd Siiri Iismaa ja tema kolleegid vastust.
Until recently, it was thought that as soon after you're born, heart muscle cells lose their ability to make new heart muscle cells, to replicate themselves, to divide.
Selliseid rakke, mis on nii-öelda terminaalselt diferentseerunud, ei ole organismis väga palju. Peale südame lihaserakud on närvirakud, kõrvakuulmisretseptorid ja silma läätserakud.
That's a very unfortunate property of heart muscle cells. If you, for example, look at the liver, if I injure your liver today, within 3 months you'll have completely repaired your liver and your liver will have restored itself. That doesn't happen with heart. So if you have a heart attack, the only thing that happens is you get a scar. And that scar can't beat, can't contract, and so the heart doesn't work as efficiently as it did before. So very recently, in the last 10 years only, it's been discovered that there is a little bit of ability for some heart muscle cells to divide, very poor compared to the liver. And we're trying to understand why it's so poor and whether we can improve that so we can get much better repair of heart once there's damage to the heart.
See on hiire süda katseklaasis. Kokku loovutab nende katsete käigus elu umbes 40 muundatud geenidega hiirt.
Mice are a lovely model. You can do lots of things with them now, and we particularly can make animals where we get the genes to make lots and lots of protein, or we can get animals where we inactivate a single gene. Of all the thousands of genes in the body, we can just make one gene that doesn't function, and then we look what happens to the mouse. And in this case, we might only inactivate that gene, not in the whole body, but just in the heart muscle, and say, what does that do? So that's the power of molecular cardiology, to allow you to ask questions like that we could never do before.
Muundatud geenidega katseloomale tekitatakse kunstlik infarkt ning jälgitakse sellest taastumist. Lõpuks loom lahatakse ja tema südant uuritakse.
On my laboratory is looking at what we call regeneration. That is the ability to repair heart muscle after injury, or regenerative response. And that's what we're very keen on, and we now have a very interesting animal model where we've been able to get around that inability of heart muscle to repair itself, and we have an animal whose heart can repair itself very well.
Ja nüüd me leiame, et südamelihase rakud jagunevad. Ja nüüd me püüame vaadata, kas nad ikka jagunevad pärast infarkti. Ja me loodame, et siis, kui me leiame, et nad jagunevad, et siis me saame leida mingisugust inhibitorit, mis takistaks selle retseptori tegevust, ja siis me saaks seda vast kasutada kliinikus pärast infarkti, kui patsiendid on haiglasse tulnud.
Ehk teoreetiliselt oleks võimalik teha ravim, mis pärast, kui inimene on infarkti üle elanud, sa annad talle seda ravimit ja tema südamerakud hakkavad taastuma.
Jah, täpselt. See on meie praegune eesmärk, jah.
I believe it's a very fundamentally new discovery. It's been known for a long time, for example, that some, and this is where comparative biology is important, that some species, like some fish, what we call a zebrafish, a little tropical fish, because it's a nice model that we study, or salamanders, like little frogs, they can completely regenerate their hearts. You can cut off part of the heart, and just like a liver, it'll regenerate itself. Now, what we have not known is why is it that the hearts of you and me, mammals, why can we not regenerate, whereas a salamander and a fish can regenerate? That's a very interesting issue, and we don't have an answer yet. We have some ideas on how that may work, and in fact, that's one of the, it's a very sophisticated idea that I haven't got time to go into now, but it's one of the major areas that Siiri, with her talents, is going to try and tackle.
No jah, seda me täpselt nüüd uurime, ega me seda mehhanismi ei tea, me teame ainult, et see retseptor on sellega kuidagi seotud. Ja nüüd meil algabki see suur töö.
So we have a theory that it's the reason that mammals can't regenerate their hearts, and this is only a theory, so don't hold me to this, is that we require our hearts to work very, very well all the time, because we have to pump against a high pressure, and the heart has to pump very efficiently. Whereas in a salamander and a fish, they have very low pressure systems. You can, even in a young fish, you can virtually stop the heart and they'll stay alive because you can get oxygen by diffusion. But you can't do that in humans. In humans and in mammals, that heart works very hard and very very exactly for a long time, and it has to. So when a heart cell divides, it can't contract because the machinery has to come apart to allow the cell to divide. So if you have too many cells that at any one time are dividing, you won't have enough heart action to stay alive. So you have a trade-off. So over time in evolution, our theory is that you have lost the ability to have a lot of cells dividing because you needed to maintain the organism alive and as many cells as possible contracting. So that's a theory that Siiri is now going to test over the next few years.
Instituudi juht loodab, et tänu suurele hulgale tippteadlaste ajupotentsiaalile ning 100 laborihiire elu hinnaga suudetakse lõpuks välja töötada protseduur, mis aitab algul kaasasündinud südameveaga imikuid ja edaspidi juba täiskasvanute välja kujunenud südamete kudesid regenereerida.
Now that's in the congenital heart disease area, but if we could now translate that into patients who've got heart attacks, and we can allow their hearts to recover completely, that'll be fantastic because we'll have nobody going on to heart failure and then dying prematurely of those diseases. We will get rid of heart transplantation. But that, of course, is a long, long way away, and that's something we hope will happen. We don't know for sure it will.
Austraallased ja eestlased elavad küll teine teisel pool maakera, aga süda on meil ühesugune. Seetõttu, kui Siiri Iismaa ja tema kolleegide tööd kroonib ühel päeval edu, ei pruugi infarkt patsiendi jaoks olla enam nii traagiline ja lõplik.